So what happened? We all know that from academic perspective, side channel analysis appeared like 1996 or so with differential power analysis, but since that's not profile, let's leave that away. And profile attacks, let's say almost 20 years ago, what was there? Well, 2002, there was template attack. And template attack was quite relevant, big thing that appeared because not only it was something new, something different, but also it's the most powerful attack from the information theoretic point of view. So extremely powerful thing. Well, immediately one can ask, if it's so powerful, why do we continue? Why do we all the time try to envision something new, make something new? Well, template attack is so powerful, only quite a lot of assumptions are fulfilled. Since in reality, many of those are not fulfilled, template attack will be often much weaker than we hope. And then over time, also some variations appeared. So for instance, pooled template attack that solved some problems with instability of covariance matrices in template attack and so on, but also stochastic models. And now this is interesting because these attacks we commonly do not consider as machine learning based attacks. They are profile attacks. Next slide, I will go into details what profile means, but commonly we do not consider this as machine learning. But actually, there is a lot of machine learning behind of this. So behind template attack is quadratic discriminant analysis. Behind pool template attack is linear discriminant analysis. Behind stochastic models is regression. So there is a lot of connection. But still, we commonly, since at that moment we did not talk about machine learning, still we kind of exclude these attacks from machine learning attacks. So what are those profile attacks that we care about? The profile attacks or two-stage attacks are exactly what the name says, attacks that happen in two stages. There is the first stage, the profiling phase, where you as the attacker has the same type of device under your control, and you use that control to learn a lot about the device. Here on the schematics, this is the identical copy part. So you have your identical copy, you learn as much as possible about your device. So in the lingo of template attack, we would say we build a template. In the language of machine learning, we would say we build a machine learning model. And then in the other phase, the attack phase, the online phase, we attack the second device under attack, where we use the knowledge from the first phase. And that knowledge actually helps us to make the attack much, much more powerful. So that's the promise of profile attacks when compared with direct attacks like correlation power analysis, for instance. Correlation power analysis is extremely powerful, but you need a lot of measurements commonly to do something. With profile attacks, we have some promise that if our profiling part is very good, we can break the target in only a single measurement. So that's the nice part about the profile attacks. There is that magical boundary, yes, if your profile is perfect, you will break the target with a single trace, under some assumptions, of course. And of course, in reality, we rarely break it with one trace, but we still break it much more with much less traces, so more efficiently than if doing direct attacks. So that's the beauty of it. Of course, on the other hand, is that part when we say, well, you need to have the identical copy of the device. What happens if you don't have it? Well, in academia, we commonly are not caring so much about it, and you will see also that in results. Commonly in academia, we say, well, there are two devices, and that's perfectly fine, but let's make our life simpler, in our head, everything simpler. Let's say there is only one device, and then we will artificially divide the measurements and say this part of measurements belongs to first device, and then the second part of the measurements belongs to the second device. So we are kind of mimicking the real setting, and we are saying, well, this is close enough, because if our attack is not successful here, in more difficult setting, it will be even less successful. So from the evaluation point of view, a valid perspective. So I said we evaluate, we do this, we do that. What exactly do we do? Well, we do the attack to see what is the performance of the attack. And how do we evaluate what the performance of the attack? Well, with metrics such like key rank, like success rate, like guessing entropy. I will not go into details, but what's important to know is we basically want to see on what position is the correct key in our list of guessed keys. So if your guessed key is very high, that means your attack is very powerful. If your guessed key is very far from best guess, that means your guessing model is very bad. So your attack is very bad. So with all these metrics, you aim to get your best guess key to be hopefully correct key, and if not correct, as close as possible to correct one. Here I just give expression how one would calculate it over probabilities, so we can discuss it later, but I will not go now. So this is general, this is profile attacks, but let's see now what happens with machine learning. And yes, I already said kind of template attacks, the custom models, this is all connected with machine learning, but let's go into clean machine learning. So what happened, let's say, 10 years ago? This is already a little bit more fuzzy because there were more papers. It's very hard to say what paper appeared first, and at one point we really started getting good results. But actually people recognize that machine learning techniques and actually supervised learning also belongs to profile attacks. So the same setting as we have in profile attacks, profiling and attacking, we get the same with supervised machine learning. Supervised machine learning training and testing, the same as profiling and attacking. And then people said, well, since it sounds natural, it should work. But of course, they also realized much more can be done with machine learning. So while even today, machine learning is most well known for doing the attack itself, but you can do many more stuff. You can do pre-processing, so various alignments. You can do feature engineering, select features, transform features. Do a lot of steps that will make your attack much more powerful. Maybe even not needing so fancy machine learning in the end, if you do good pre-processing. So this is also the part of the promise of machine learning. There are many techniques, many different goals. So it's not only about the attack, but about the whole environment. So what is machine learning? Of course, I will kind of almost skip this slide, but it's a field of study that gives computers the ability to learn without being explicitly programmed. What does it mean for us in SideChannel? It learns how to classify the S-box outputs or round outputs to a certain classes labels without being explicitly programmed to recognize it. This maps to this maps to that. So it's a way how we can ease our life and do pattern recognition in a very efficient way. So what are the types of machine learning? What do we actually use? Because machine learning is huge. So here are just some types of machine learning. So this is on the basis of the feedback. There is the supervised learning, there is the unsupervised learning, semi-supervised learning, and so on and so on and so on. If we talk about side-channel attacks on symmetric key crypto, commonly the main role is supervised learning. If we talk about public key crypto, people started more with unsupervised learning with various clustering ideas. And more recently, actually, people are moving into supervised learning even for public key crypto. And semi-supervised is some strange setting like supervised, but with not a lot of measurements. So you can still do something. I will just give a rough estimate. Supervised learning inside channel, I would say 95% of papers. Unsupervised, couple of percent. Semi-supervised, I know 2 papers that do semi-supervised for side channel. And actually, it's very strange setting because, of course, it's a weak attack, but still doing something, so people are not clear what to think about. So since supervised learning is the most important, what is it? Well, we have our training phase, we have our profiling set, we have our training pairs, X and Y. X are the traces, Y are the labels, so S-box outputs or round outputs or Hamming weights, Hamming distance of those values. And then X is commonly known as the feature vector because every value in that vector is a feature, and Y is the label. And our objective is to find a function f such that y is equal to f of x. And then if y is a real number, we talk about regression. If y is a Boolean variable, we talk about binary classification. And if y is a member of a finite set, multi-class classification. And actually, you can see that mostly people today do multi-class classification. And for instance, in the setting of block ciphers, we mostly check what happens with AES. And then in AES, you would commonly have 9 classes. So multi-class classification with 9 classes. If you have Hamming-weight, Hamming-distance models, or 256 classes if you have the S-box output model, identity model. So this is the setting: supervised learning, classification, and multi-class classification. And this worked very nice. Actually, on one of the last slides, I will also show you a couple of excerpts of various papers doing the techniques here. But what's important to note, people played with a lot of techniques, but those techniques are only a small part of what there is. And still, techniques like random forest, like support vector machines, worked quite well, and it was very successful. People also used, I will immediately say, multi-layer perceptrons, and this is also one interesting question. I'm not really sure, honestly, at one point, multi-layer perceptrons were really used in deep learning versus they were just used in machine learning. So when is a multi-layer perceptron a deep learning? When it has more than one hidden layer. But we can notice that in older papers on side channel analysis in multi-layer perceptrons, researchers commonly do not mention the number of hidden layers. So actually, it's very difficult to know, is it machine learning, is it deep learning? But what is deep learning? And why do we do it? So here I put the title 4 years ago, and then question mark, because I really do not know when it started. Convolutional neural networks appeared 2016, so that's why I write 4 years ago. And why do we like deep learning? Because it can reach top performance, even if device is protected with countermeasures. I will not talk much about countermeasures because we have only 30 minutes, but they are masking countermeasures, they are hiding countermeasures. But deep learning works good for both aspects. And we like it because it works great, of course, but also because it allows us to be a little bit lazy. Because with common machine learning, simpler techniques, we need to do those feature engineering pre-processing steps. Here with deep learning, we commonly just input the raw features and we leave everything for the algorithm. So it allows us to skip one phase and just leave it for the algorithm. This is also one very nice part why many people like deep learning. But that, unfortunately, at the same time also means we do not know how to explain what's happening inside deep learning very well. So how do we build common deep learning things that appear inside channel? Well, we start with a neuron. We make many neurons, we connect them. This is already called multi-layer perceptron because we have multiple layers. And then this is one example of our neural network. So you can see here I write many hidden layers under quotations. It's not so many, but think of it like crazy many layers. But we can also do a network of this shape. Only one hidden layer and many neurons. Again, these number of neurons are not so huge, but think of it like having thousands and thousands, tens of thousands of neurons. And then it's also a difficult question to say, well, what architecture would be better? Do we take one? Do we take the other? So this is also opening a lot of perspectives how to make the best architecture. And this is one example of, let's say, common convolutional neural network inside channel analysis. What can we see here? Let me tell you immediately, this is not the best neural network there is. It's one common example up to last year. But what we can see here that actually this neural network is not very deep. So it's a couple of convolution layers, it's a couple of pooling layers, little bit dropout, little bit batch normalization, but nothing much. And still works great. And actually, this same architecture worked great to break a lot of different implementations of AES with and without countermeasures, hiding and masking countermeasures. But this architecture also was used to break public key, elliptic curve cryptography with only a single measurement in the attack phase. So quite general structure in a way, and still able to do a lot. But actually, where do we stand if we look at the big picture? So this is the big, let's say, big picture. First is AlexNet, where almost everything started seriously for convolutional neural networks. Then VGG, the architecture I showed you is also the VGG type, and then ResNet. And here you can see the ratio of the sizes. These sizes are really correct, so ratios are correct. And now I can tell you the network I showed you is somewhat smaller than this VGG. And up to recently, that architecture for side channel analysis worked great. And even more recently, researchers made much smaller architectures that work even better. So we are very much somewhere around here. So this already tells us, okay, we do deep learning. And there is a reason why we do deep learning. But deep learning we need versus what deep learning are used in other domains, it's very much different. So we are very much script kiddies for many other domains when regarded from the size of the network that we need. We can use bigger, but apparently, at least for now, there doesn't seem to be a lot of need. So what are the common results? These are just coupled to give emphasis on stuff. So here I write, I depict 4 commonly used data sets. So this is also one of the big issues for our domain. We do not have good publicly available data sets. Well, we have some and they are good, but we do not have many. And when you are very limited in data sets you can use, you are never sure if what we are doing is really the best way how to do it. So here you can see DPA contest V4 data set. This is the common one people start. This is something you can see also from how the features look like, the importance. This data set is very easy to break. Then you have some data set like this. This is very noisy, quite difficult to break from that perspective. Both of these data sets commonly do not have any countermeasures. Then you have something that has a hiding countermeasure, random delay countermeasure, so something happening in the time domain, and ASCAD that has a masking countermeasure, and today most of the researchers take ASCAD as the standard data set to do the test. So let's say these are the common data sets people consider. And I will not again go into details, but for instance, this is one depiction of the results you get with that DPA-V4, that very easy data set in deep learning. So we can see we break the target with 2, 3, 4, 5 traces. In essence, extremely easy to break. Even something masked, we still break it with a couple of hundreds, and these results, like I said, are not even state-of-the-art anymore. So I think now you can probably break it with half of this time. So we are already quite mature in breaking the data sets that we have publicly available. And of course, this is the deep learning for breaking the targets. But we can luckily do still some other stuff. You remember I said we do not need to do pre-processing because deep learning will do everything for us, but we can do pre-processing. And actually, I think this is one of the more interesting directions to go now. How to do good pre-processing for deep learning to make the attack even better. So for instance, here, this is the ASCA dataset. And here we also, to ASCA dataset, we added the random delay countermeasure. So random delay interrupt. And this, since we implemented it in a quite difficult way, this is very difficult for the neural network to break. So you can see even the best attack, let's say template attack or CNN, guessing entropy is not very good. Guessing entropy of 50 will not bring you breaking of anything. But then, look what happens if we add convolutional autoencoder, something that pre-processes and basically learns how to remove the noise from a measurement. From something that is extremely difficult to break to something that is extremely easy to break. So this is, in my opinion, very interesting perspective for us that are interested in deep learning and side channel to go beyond attacking, only attacking. We need to think what more can be done. What are the new interesting directions we can take that really have promise of deep learning, and there are not other techniques we can actually use. And also, this is what I told you, we cheat. We cheat in academia by simply saying, well, we take one device and we pretend those are two devices. But is that really the case? Well, here I depict one attack with multi-layer perceptron with deep learning when we do cheating, when we attack basically the same device with the same key. So you can see guessing entropy around 2, 1 or 2. Extremely easy to break. So no problem at all with 2 traces to break. And this is very easy target. But this is what happens if you attack different device. So the same type of device, but it's 2 different samples, and they have different keys, because that's reality. The key you have on your device would not be the same as the key as you have on the attack device. Otherwise, that would be very strange. And here we can see that for many attacks, we are actually not even able to break. So this tells us that from one side, our results with deep learning are great, and we are pushing forward, and we are saying we are managing to break many stuff very easily. But on the other hand side, we see, well, we are far, because we do some assumptions that are not reality. So it's an interesting way how to connect between those two. And I'm more or less on time. So let me give you a little bit on the conclusion part. So this is just a slide I prepared some time ago, so it's also not the latest, up to date, with papers that consider machine learning for attacks. And you can actually see what, well, first, it's quite decent number of papers. There is a lot of research happening, and most of these papers happened in the last couple of years. And also from the other side, we can see that the number of techniques that people really use is very limited. Supervised machine learning has dozens, hundreds of techniques. Here we have 1, 2, 3, 4, 5, about 15-ish techniques. So we actually tried only a small part. And I'm not saying we need to try everything, but the question is, did we try really the most important, the best choices? That's a big question, because there is also the no free lunch theorem saying there is no single best algorithm for all the problems. So it's maybe too much to expect we can find one algorithm for all our data, but should we also expect that there are no better algorithms in general? So it's an interesting question to see what is the number of exploration versus exploitation. At what point do we say, fine, I do not want to explore any more machine learning techniques, any more deep learning techniques, but now I really want to learn that deep learning technique and use it in the best way. Because a big part of it, all these that I actually completely skipped up to now, is the hyperparameter tuning. The more complicated techniques you use, they have more hyperparameters, more settings you need to select. We talk about deep learning, and I said hidden layers. Okay, how many hidden layers? 1, 2, 3, 4, 5, 55. So AlexNet has 8 layers, but ResNet has 152 layers. How do you select? Well, only with a lot of experience and a lot of experiments. So there is also that trade. And also what I want to say, why are deep learning techniques working so nicely for those publicly available datasets? So when we talk about hiding countermeasure comes in the time domain. And there, for instance, something like convolutional neural networks work great. Why? Well, because convolutional neural networks have the property of spatial invariance. So for convolutional neural network, that random delay interrupt, that change in the time domain, that misalignment, if you want to say it like that, does not pose a problem. So convolutional neural network is inherently adapted to fight against countermeasure like that. And on the other hand side, what happens with masking? Well, let's think, how do we attack masked data set? Well, we do higher order attack. What is higher order attack? We combine the features. We try to combine the feature on the value and on the mask. But isn't that what fully connected layer in multi-perceptron does? It connects every feature to every feature. So you do get the same combination of all the features. So you do combine both mask and the sensitive information. So that's why deep learning is quite adapt to both masking and hiding, because it does something quite natural. So what are the challenges? So this is the part when I said, what are the challenges we need to explore? Well, how do we select those machine learning techniques? How do we do our hyperparameter tuning? Many people do random search or grid search or this or that, and we are actually not even sure how important is it. Do we really need to tune around, or can we just do a couple of experiments and be done? Then there's portability, one device versus two devices. A lack of data set. This is what I already said. Interpretability, explainability. I think this is extremely important aspect. Not only having the attack, but knowing why the attack works. Interpreting the results and explaining the neural network, that's a big challenge. And of course, that's a challenge for whole machine learning domain. So one would say, well, this is too much for us to solve. But we are limiting our attention only to a small number of problems. So for us, it's easier because we do not care about image classification, this time. We are very limited in what we care. Big problem, there is no clear connection between machine learning and side channel metrics. So when you do your side channel attack, I said you care about key rank, you care about guessing entry success rate. But when you do your machine learning training, you care about accuracy or loss or something like that. If you have a good accuracy, does it mean you will break the target? Not always. Just in your Hemingway scenario. Hemingway, you can have your machine learning algorithm telling you everything is Hemingway 4, and your accuracy will be 27%, because all the numbers between 0 and 255, 70 numbers has Hemingway 4. So 70 divided by 256 is 27%. So you can have extremely stupid machine learning algorithm, or smart if you want to look at it from that side, but that will not help you in breaking. So what kind of metrics do we need for our side channel? And then countermeasures. How do we work with countermeasures? How do we work against countermeasures? Also, one important thing, we are solving problems that we already know how to solve. We are attacking data sets that we knew how to attack even before deep learning. So we also need to go further. We need to look at the problems that we do not know how to solve with other things. This is the challenge. Not only doing like other people did and something better, something new. We are very much lacking any kind of methodology, any kind of framework. How do we set our experiments? How do we say this is better, that's worse? So quite a lot of open questions. And also some more general thing, where do people use machine learning in general in cryptography? Because let's say implementation attacks cryptography. So side channel we talked. Also, you can easily use it in fault injection, but also modeling attacks on paths, detecting hardware trojans, machine learning over encrypted data, topics like that. But also for cryptanalysis, people they are trying machine learning for factoring numbers, for designs of ciphers. So there is a lot of aspects. What we need to be aware is that machine learning algorithms do not know what they are doing. We feed them with data. Machine learning algorithm does not care, is it crypto data or is it image? So actually, we can use machine learning techniques for a wide variety of problems. The question is to recognize those problems that are realistic, that we need to solve, that we do not know how to solve better. That's the challenge. And finally, yes, machine learning, in my opinion, plays very important role in cybersecurity, and that role will just go up and up. Why? Because in the end, what do we want? We want good results in an automated way. We want to exclude a chance of human error. We would like the attack to work on its own. We would like the design to be done automatically. So avoid the human error, make it faster, make it easy. And Today, in implementation attacks, machine learning does represent, it seems, the most powerful option. People are very happy with the results. But still, what we need in a side channel, at least currently, seems to be much simpler than what we need in other domains. And of course, there are many, many parts of knowledge from other domains we can reuse. So my advice is, before trying to invent something completely new, see if someone tried to solve the same problem, other domain, but same problem. Probably yes. Our problems are not so unique. So there is a good chance there is already a good solution somewhere. And final point, which I think is extremely important for all of us to think about it, why are we in the game of attacking? We are in the game of attacking so that in the end, we can design more secure devices. So when we are using deep learning for attacks and breaking targets, that's great. But how does our new attack teaches us how to make the better design? If I tell you my deep learning broke this target, amazing. But how can I use that knowledge to make a better countermeasure in the future? So this is something we need to think about. What is it deep learning doing, and how do we make better products in future? Because in the end, that's the game. We are in the game of making more secure products, and we evaluate it with side channel attacks. And thank you for your attention. I do also have, wait, let me just stop sharing and start sharing. I just want to share, this screen, this is also, I hope, very interesting and very simplistic example of what I want to tell you. When people started the template attack with stochastic models, actually, the settings were frameworks for development were much less developed. And if you wanted to do attack, you really needed to do some coding to do a lot of preparation. But think of it, today, if you want to do a machine learning attack on side channel, what do you need to do? Well, you need to load the data set. You divide the measurements, couple of lines of code. And for instance, I show the code for support virtual machines, for multi-layer perceptron, and for random forest. So attacks, we need 3 lines of code, 5 lines of code. So that tells us people, even without a lot of knowledge about side channel, about machine learning, can easily do attacks. And that's very nice part, because we are getting more and more people interested. But we should not avoid the fact that we need also to know what is happening. So while it's good just to be able to copy and use the code, we need to think what the code does. Why is it good? And let me show you one more example. So this was very simple machine learning techniques, but even if we go for something, let's say, a little bit more complicated. So this is the full code you need for your deep learning attack in Keras. Fine, you can make your network bigger, you can make this, you can make that. Actually, this code even has several different networks. So 150, 160 lines of code, you have the full attack, you have the very efficient attack. See, here we have the key rank example, even something that runs relatively fast. I run it on a laptop that does not have any GPU. So it's just, well, discrete GPU. It's just Intel graphic card, and it even runs this. And it's a convolutional neural network. So we can see that we can do powerful attacks with not a lot of knowledge coding-wise or even very specific equipment. And this is nice because it gives us all opportunity to learn and to do more stuff. But we always need to be careful. Why are we doing something? To have good motivation, to have good intuition. How does it make sense? And with this, I do open floor for questions. I think I was exactly on time.
Yes, perfect timing, Stjepan. Thank you very much for your presentation. Yes, now it's time for Q&A. You can open, if you open your chat function, then you will be able to put a question. And everyone, please feel free to send your questions to Stjepan in the chat, and he will be able to answer them right now.
So first question is, do you have pointers to open source frameworks for machine learning, deep learning against side channel that we can try on available data sets? So from dataset side, there are, I know, 5 or 6 publicly available datasets. I would recommend checking any of the latest papers published on some of the top conferences like CHESS. Commonly, people will write links there for all those datasets. So those would be something like ASCAD, DPAV4, AES-RD, AES-HD, and CHESS CTF from CHESS 2018 competition that risk will be. So this is what people mostly do. Open source framework for machine learning, deep learning. I do not know any framework really for this. Why? Well, I believe the biggest reason is it's very simple to do side channel with machine learning, so people did not really build big frameworks. I know, for instance, my group is now building a framework. Hopefully it will go out in a couple of months, then there will be something. But currently, many of the papers do publish their own architectures. So if you go, for instance, on the ASCAD page, you will not find only data sets, you will also find very nice multi-layer perceptron and very nice convolutional neural network. But really a framework in the big picture, I do not know for side channel with machine learning deep learning. What performs better, CNN or RNN? So CNN is convolutional neural network, RNN is recurrent neural network. This is a very good question and tricky one because currently the answer is very simple, CNN without a question. So all the results we have publicly available indicate that CNN works great, and unfortunately RNN does not work at all or works terribly bad. And this is in a way quite counterintuitive because one would say, well, what is our side channel measurement? It's some time series, something from the oscilloscope, and RNNs, because of their recurrence, they should work quite nicely with time series. But it does not seem to be like that, and it seems that the problem is that the recurrence setting usually takes too small period to take all the important information. So currently, RNNs seems not to be a strong option in side channel analysis. I must say from the other side that there are not many available results. I'm aware of 1 or 2 papers in general that even tried RNNs. So we do not have many results. Maybe we do not have more results because people tried and did not succeed. But what is available, it did not work well. Will deep learning help for side channel for higher clock frequencies rather than lower frequency microcontrollers? I see lots of processing and noise in modern SOCs. Well, this is a very good question. I would say, I hope yes, but this is extremely good question because we do really see that we, from academic perspective, are in the setting of thinking, well, machine learning, deep learning works great. Our results are amazing. But when you talk with people from practice, from industry, commonly you will hear quite a lot that they say, well, honestly, this doesn't really work in practice. When you do a difficult target, it doesn't work. And now big question is why? So I would like to say that I think and I believe it will help, but there is a big road up to that point because first we need to obtain as a community data sets with those measurements, and only then we can really do the attacks and see how well is it going and improve and improve and improve. I would say from first, probably it will not work good, but I do hope it's definitely doable. Maybe for those targets, we will finally need to go to real deep learning, big networks, hopefully. But I have hopes that it should work. Okay, no more questions, people. Do ask something.
Yes, everyone, this is your last chance to ask Stjepan a question for today.
Not the last, but you
Okay,
can
last.
What city is in the background? Excellent question. So this is Zagreb. So I was chairing the Eurocrypt that was virtually held in Zagreb. So I had Zagreb in the background. So whoever comes next year to Eurocrypt, if it happens in real, Yes, let's hope. Then it will be in Zagreb. So this is actually the view from the top floor of the hotel where we will have our reception party. So this is the real view you can enjoy it there. Beautiful city. Oh, okay. I live there, so maybe that's why I do not appreciate it so much. But yes, I heard it's beautiful at least for tourists. Yes, let's say it like that. Which nice book to start with? Advanced DPA theory and practice towards the security limits of secure embedded circuits. Yes. So book-wise, there is not so much, I must be honest. The extremely nice book to start is the Blue Book, so revealing the secrets of smart cards. But that's 2007. That book does not have anything specific for machine learning. So I would say the best reference for really state-of-the-art results is checking the proceedings from one of the top conferences like, I don't know, chess or DAC if it's a little bit more on the hardware side, or date or something like that. So any particular good countermeasure against machine learning DPA? Very good question from several people. It does not seem so that there is much done up to now. We are still in the setting, like I said, the problem is that academia versus practice, that we in academia think we are already crazy successful, that people in industry think, well, you are not so crazy successful with top results. So the question is, I do not even know which state-of-the-art countermeasures that are commonly used on targets that are commonly used that would be very easily breakable anyway. But I do not know any of very specific results going for something very, very much against machine learning. The one paper I know is to use, for instance, you could use a noise that makes adversarial examples, because adversarial example is something that makes machine learning suffer. So if you can make a countermeasure that produces noise that pushes examples to become adversarial examples, that could be very interesting countermeasure. The biggest problem with something like this is in practice, it should be very difficult to make a countermeasure that behaves like that. But that would be one very, let's say, exotic and cool direction to go, in my opinion. I'm a bit concerned about the published results in some papers. Due to the nature of deep learning, it's hard to retrieve the results. Can you comment on this or have your solution? I completely agree. There is a big problem with that. And unfortunately, commonly, many people do have very simple answer that is, in my opinion, very wrong. Why? Because they say, well, we are side channel people. We are not machine learning people. So if we are a little bit imprecise from machine learning side, it should be tolerated because it's not our background. And then indeed, many of the results are very difficult to recreate. And that is a problem we have as the community. But this is also the problem that we recognize as the community, and we are working to improve. But the best, simplest solution is really what many people are doing. They do publish their best architectures. So you can now find quite a lot of machine learning models online, or at least architectures, if not the whole models. And then it's quite trivial to reuse that code and see, well, I do not get the same results, then there must be something very strange. So I would say the current best solution is for people to really do offer their architectures online, especially if people are claiming those architectures are great. Then it's very nice to share it with other researchers that we can also use it and explore it. I'm very grateful to people behind ASCAD and some later papers. They really published their architectures, and I do use those architectures in many experiments because it's very natural to use it, and then you know for sure what you use is what they describe. Any details about your trace collection, measurement, setup, and targets you have tried? About exactly what? So for DPAV4, it's a software implementation, mask implementation that has some problems. So it's basically a mask implementation. So it's AES 128. I do not remember more details. ASHD is FPGA implementation with very low signal to noise ratio without countermeasures. ASRD is software implementation, random delay interrupt, and ASCAD is again software with masking. So I do not talk about the setups there because none of those data sets are mine. So I did not really do the acquisition. The results I showed you for portability, so the differences there are done with AVR, and the setup is EM measurements, several oscilloscopes in parallel, all doing the measurements at the same time. The oscilloscopes were LaCroix, the EM probes were Langer. And for more details, I would recommend send me a mail, and I will give you exact links with all details, because I do not remember all the details about the measurement setup, honestly. What should be included in a perfect data set? There are many masking schemes, many measurement methods. So perfect for attacker or perfect for designer? Let's say perfect for the attacker. Perfect for attacker means no countermeasures and very nice example. But let's say perfect for evaluator, perfect for us as researchers. I would say that the amazing setup would be the same algorithm, let's say AS128, just to make it simpler, done in portability settings, so on 2 different devices, with and without countermeasure. So countermeasure on, countermeasure off, because that gives us a lot of options to explore. Because if you want to play with one device, you take measurements for one device. If you want to do portability, you have with countermeasure, without countermeasure. Countermeasure wise, I would recommend to have, well, this is a lot of work, but unfortunately we need it. We need a strong masking countermeasure, and we need a strong hiding countermeasure. And then we would need a setting without countermeasure, only hiding, only masking, and ideally even both, because we want to see what are the limits. Currently, we do not know what are the limits of deep learning. We think deep learning is great and breaks everything because what we do is too simple. So I would say there is not a single perfect data set. What would be perfect is actually to have quite a lot of measurements that do have relatively small differences between each other, so that we can really evaluate the effect of something small. Okay, what's the effect of portability? Well, I can do that only if I have exact setting for portability. What's the effect of masking? Only if I have everything fixed and then only mask on off. So it's quite a lot to work. And currently, I would say, I do think that masking countermeasures do give better, stronger results than hiding, it seems, although hiding is also not very explored. So I would say this is the direction that seems more interesting for people to look. But anything would be very helpful. We are so limited with what we have that anything would be helpful, honestly.
Okay, I think we're getting to the end of the session. So maybe time for one more question, if you have one more question, and then we'll finish.
Well, if there are no more.
Okay, so that was a perfect timing then. Thank you very much, Stjepan, for your presentation and for answering all the questions. Yeah. Always a pleasure to have you at hardwear.io. And we hope to see you in future editions as well.
I have something smart to say anymore. Too many topics to talk about. So just a last message to all the people. I covered only small parts. So if you are interested in any of these, you have my mail. Do send me mail. I will do my best to answer. So I at least point you to papers, to data sets, to architectures. I will do my best to help if I can. So just write and let's talk.
Great. So feel free to reach Stjepan if you have any more questions.